to be using a theorem, but I have to prove why it is so. Am I making sense? So I will write the statement properly. Let's move to this. Prove that there are infinitely many primes. What are primes? What do I mean by primes?
That's only the cells at one.
Prime numbers, what we call prime numbers. Yeah? That number, you don't have to include it. Okay? Instead of saying prime numbers, you can just say primes. Okay? Such that P is a prime number, or such that P is prime. It's the same thing. It's just like saying odd number and odd. You can use both of them interchangeably and it's okay. Okay? So, there are infinitely many primes. So, the contrary will be what? What will be the, there are what?
There are
Finite prime. So we will say, suppose that there are finite number of primes. Because they are finite, we're going to assume there are n of them. You can use k of them, you can use t of them, it doesn't matter. Okay? Suppose there are n finite prime number. Let's put it that way. Suppose there are n finite prime numbers p1, p2, p3, up to pn. All are integers, of course. Does it make sense? So, the technique is to try to follow through in your calculation and run into something that is illogical at the end of the day. So what we will do next is to say, we pick a number, let's say n, maybe I change it. We pick a number, say x, because we have been saying so much, too many n, which is the product of all these prime numbers, okay, up to pn plus 1. The idea is to now pick a number, all the prime numbers that we have, multiply them and add 1. Of course, we can have so many of these. If you multiply the first 3 prime numbers, let's say there are only 3 prime numbers. 2 times 3 times, what's it called now? 5. What are those numbers? What is that? That's 60. No, 30. Right? Then you add 1 to it. What do we get? 31. Is 31 a prime number? Then the assumption there are only 3 prime number is wrong. You must be able to show that the other number, it may not be a prime number. You could either show that it's a prime number or something is wrong with it. What do you notice about, I think I was discussing with you. Numbers are classified into 3 categories. Who can tell me what they are? Integers are classified into 3 groups. But let's say positive integers to make it easier. A positive integer can either be a prime or, give me the other 2 classifications. Unit and composite. Prime, unit, and composite. I will start with unit. Unit means 1 factor. Prime means 2 factors. Composite means more than 2 factors. So, what positive integer belongs to this group? 1. Okay? And this is where the prime numbers are. 2, 3, 5, 7, 11, 17, 19, and so on. Every other one belongs to the group of composites. Sorry, this is composites. So composite like 8. Okay? Now, every composite can be written as product of primes. This you did in IGCSE. They give you something like this. 5 express 50 as product of prime. Do you remember this question in IGCSE? Then you have to write 2 times 5 times 5, something like this. This is composite. Every composite can be decomposed into product of primes. Okay? Now, if you end up adding 1 to it, do you get a prime or do you get a number that is still not a prime, okay, but not unit? Do you get another composite? It's possible. Do you understand? Because if I do this now, and I had, let's say I do 3 times 3 times 3, which is what? 9, right? Do you agree? No, 27. and I decide to add 1, do I get the prime? But I multiply prime numbers, isn't it? And I added 1, but I don't get the prime. So I'm not saying that this is going to be a prime. I'm only saying it's definitely going to give you something that is suspicious. Now, the idea is this. For any of these, can you divide, is any of these P1 to Pn divided by x, divisible by x? Or is x divisible by any of the prime? Can any of these prime divide this successfully, divide the number x successfully? Talk to me, please. Why do you say that? You have a 1. So when any of these prime numbers, remember we said there are finite prime numbers, and these are all the prime numbers. Okay? If we are able, pick any composites that you have, let's say 10, a prime must divide it. Isn't it? This number is definitely not 1, so it doesn't belong here. Right? So if indeed these are all the prime numbers we have, then it is a composite. If it is a composite, then one of the prime numbers that you have so far must be able to divide it. Do you agree with me? Let's pick 10. If 10 is a composite, what are the prime numbers before 10? 2, 3, 5. One of these at least must divide this number. Okay? You pick 12. What are the prime numbers before 12? 2, 3, 5, 7. One of them must divide it, yes?
Yes.
Okay? Now, if I decide to add 1 to this, then I get the prime number again. If I add 1 to this, I get the prime number again. Remember, when I added 1 to this, I get the composite again. In any case, if you cannot divide it, it's either it's a prime itself or what? Or a composite. Do you get the point now? If you multiply the primes and you add 1, and prime numbers cannot divide it, there are 2 options. If a prime number cannot divide it, then it must be a composite.
Yes.
Okay? Or no, if a prime number cannot divide it, it's not a composite. Of course, if it's a composite, a prime number must divide it. If a prime number cannot divide it, then it must be another prime itself. Basically, that's what I'm saying. Because if you look at all the prime numbers, 2, 3, 5, 7, 11, 13, 17, pick any prime numbers and look back to see if another prime number can divide it. Is it possible? But the moment you pick a number that you call a prime, and you can find a prime divisor, that disqualifies it from being a prime. Do you get the idea now? Because prime numbers should only have 1 and itself. And if you can find another number that can divide it, then there's a problem. So if you are able to trace all the prime numbers and they do not divide a number you are looking at, then that number must either be a prime number itself or a number above a prime number. Which means, and if the number extends beyond this list of prime numbers, it's possible we still have some prime numbers that we have not accounted for. But in this case, we assume that all the P1, P2s are distinct. They are different. If they are different, and none of them can divide this number, then this number has to be another prime again, basically. But remember, I didn't specify that they are actually distinct. So if they are not distinct, then this is a case of this. Okay? And what is this number giving us again? 28. Now, if we claim that there are only, maybe the largest prime number we have is 3. Well, let's see. 2 times 3 times 5. What do we get? 30 plus 1, okay? If I use this, I get that. Let's say 7. I'm trying to see how I can give you. Anyway, let's quickly continue with this. So from here, the first thing we want to mention is x must be more than all the prime numbers. Do you agree? Instead of writing each of them one by one, you say x is more than maybe pk. For k equals 1, 2, 3 up to n. Do you understand this? That is, x is more than all the prime numbers. That's one thing we know. Also, for K still, I don't need to repeat it because it's already there. So if I say pk again, we know what that means. Also, none of the pk divides x. Do you agree? None of the pk divides x. And we expect this number to be composite. If it's a composite, at least one of the prime numbers should divide it. So this is your contradiction. If you claim these are all the prime numbers, any number you form, you don't expect it to be a prime because it's clearly not a unit. If it is clearly not a unit and you don't expect it to be a prime, then it should be a composite. If it's a composite, at least one of your prime numbers should divide it. Then this is wrong because none of them actually divide it. Am I making sense with that? So this is where the contradiction comes in. So I'm going to write it as a statement clearly now. Any questions, please? Let's quickly write 2 minutes. So the explanation that I've said is written now as a statement. Please, I only need 3 more minutes of your time. Sorry, you're going to probably be late to lunch. All the other questions, please send me messages on WeChat once you practice and you run into something that is not clear to you over the weekend, so that you can be well prepared when you come back on Monday. All right? Now, I've given you practice questions. I'm not saying these are the questions. I actually brought that to class thinking we'll have enough time to go through as many of them as possible. And most of these questions are not the questions we have done in the class. So please do not just rely on this and thinking this is it. But I try to combine different proofs categories. Unlike previous worksheet, they are strictly contradiction on this, induction on that, but this is like combination of all the proofs that we have done. Okay, so please rely on all the 4 worksheets. So quickly, please listen. Crystal asked me this question over the, I think last week, something like this last week. So I wanted to just clear some misconception that I observed, although I think she now understood what to do for that particular question, not this one. So I noticed that many of us have problems with series in induction. We are okay with proof by it is divisible by 5. We are okay with inequality problems. We now know how to manipulate those. But now when you have a long statement like this, in form of a series, some of us still have problem with the process. So that's why I wanted us to quickly look at it. Now, if I assume this statement is Pn, so let Pn be the statement. And this is where the misconception is. P1, so I say for P1, which means when n is 1. You consider this term and when n is 1. So you consider the n here is the number of terms on the left and the value of n on the right. Because the statement says when you add from 1 to 2 to 3 to n, is the same as substituting the n here. So if I add the first 5, that is putting when n is just 5 here. Okay? So for P1, left hand side is simply add from the first term to the first term. That's just the first term. And that is 1. And your right hand side is substituting n as 1. And you get, so that is to say that the statement is true when n is 1. For P2, now this will be clearer now. Your left hand side means you had from the first term up to the second term. So which means it is 1 cube, oh why did I say squared? Okay. 1 cube plus 2 cube, which is 1 plus 8, which is 9. And the right hand side is when n is 2. That is 2 squared, 2 plus 1 squared, divided by 4. Of course this cancels and you get 9. So it is true for P2. Now your inductive hypothesis is to just say, assume, I was checking an IB mark scheme, it says do not accept when n is equal to k. Rather, accept, assume it is true, because that was quite funny to me. Assume it is true for n is equal to k. Because maybe what they are trying to say is that students are not supposed to tell us it is true by saying, oh, when n is equal to k, this happens. But you are trying to say, let us assume it is true when n is equal to k. Okay? I will take a picture of that mark scheme and I'll send to you on the group. Assume it is true for n is equal to k. That means 1 cube plus 2 cube plus 3 cube up to some point k cube is the same as when k is substituted. In your math induction, your inductive hypothesis is very important. We must see it and we must see how you use it in the next step. And the next step, which is the final step, is to now prove when n is equal to k plus 1. So to prove n is equal to k plus 1. So when n is k plus 1, you want to say, so this is what you want to prove. I like to write it out first so I know what I'm up to. Okay? When n is equal to plus 1, I'm trying to show that 1 cube plus 2 cube plus 3 cube up to k plus 1 cube, basically, yes, equals k plus 1 squared. Then k plus 1 plus 1 is k plus 2, am I right? Divided by 4. Now this is what I want to prove. I'm just writing it for convenience. Your proof now begins by saying the left-hand side of what you want to prove. The left-hand side is 1 cube plus 2 cube. When I'm writing my left-hand side, I like to write the step before it. You can tell me why that is necessary. So you can substitute neatly. Now this is your inductive hypothesis. If we do not see how you use your inductive hypothesis, you have not even proved by induction. So apart from P1, you must do this and you must be able to do this. These are the 3 major steps that are very important. What? Q. Apologies, I'm just rushing. Which one? Okay. So if you put this in, k squared, k plus 1 squared, divided by 4, then k plus 1 all cubed. And this you must simplify. Let's quickly simplify quickly. From these 2 terms, you agree k plus 1 squared is common, isn't it? Yes? What do you have left here? I have k squared over 4, yes? And on the other side, I have k plus 1. Okay? So which means this other side will be k plus 1 squared, k squared plus 4k plus 4, yes? Is this not a perfect square? That is k plus 1 squared, k plus 2 squared, everything divided by 4. Which is your right hand side? Hence, the proof. If you do not show this logic, you do not apply your inductive hypothesis, you do not state your inductive hypothesis, you have not proved by induction. Thank you very much.